After studying this module, you shall be able to understand the dynamic stereochemistry of cyclic and acyclic systems. You will be able to explain the change in the reaction rate with respect to different stereochemistry of reactants and reaction intermediates. Let me now introduce you the dynamic stereochemistry. Dynamic stereochemistry deals with the effect of stereochemistry on the rates of chemical reactions. This involves the bond making as well as bond breaking and also the conformational transformations. It also correlates the stereochemistry of the starting reactant and the products in terms of transition state as well as intermediates. It has been recognized that the distereomers differ significantly in their chemical reaction with respect to relative rates and sometimes the nature of the products as well. The classical stereochemistry is not appropriate to answer questions related to rate of chemical reactions. The conformational theory not only provides a logical basis of these observations, but also provides information regarding the relative reactivity of stereoisomers. To understand the relationship between the reactant and the corresponding product stereochemistry, the studies of two reactions are important. Let me tell you which type of reactions. It is stereoselective reaction and stereospecific reactions. Let us see what are stereoselective reactions. Stereoselective reactions are those reactions in which the reactant predominantly forms one stereoisomer preferentially rather than the other stereoisomers. For example, the bromination of cyclohexene gives only one product, that is trans 1,2-dibromocyclohexane as shown in the scheme given here. Addition of bromine to a double bond is an anti-addition. That means it is happening from completely diagonally opposite sides. The two bromine atoms are adding from diagonally opposite sides of the double bond. And it proceeds via the formation of a bromonium ion. Since cyclohexene exists in cis isomeric form, it cannot exist in trans isomeric form, it has to have a cis stereochemistry. So it leads to the formation of such type of an intermediate in which the front side attack, that is the top face of bromonium ion, is completely hindered and there is no formation of the cis product. Thus, this reaction is the example of stereoselective reaction. Now understand what is stereospecific reaction. The stereospecific reactions are those reactions in which the reactant can exist as stereoisomers and each of the stereoisomeric reactant on reaction gives a different stereoisomeric product. And these reactions are the results of reaction mechanisms. For example, addition of bromine to cis or trans 2-butene, both of them are stereospecifically trans. That means the addition takes place in a trans manner. For example, let us see the addition of cis 2-butene gives a racemic mixture of 2,3-dibromobutane, while addition to trans 2-butene gives a mesostereoisomer, as shown in scheme in front of you. Hence, these reactions are called stereospecific reactions. Both the isomers are reacting in a very specific way. Cis 2-butene adds bromine either from the top face or from the bottom face to give the bridged bromonium ion. This intermediate is attacked by the other part of the reagent, that is the bromide ion, either via the path A or B as shown in the scheme here, or via the path C or D to give equal amount of enantiomeric pairs called racemic mixtures. On the other hand, the trans 2-butene gives only the meso product. This is also shown in this scheme. Any path will ultimately lead to a meso product. Now, dynamic stereochemistry of cyclic and acyclic molecules. Let us see what happens in their cyclic as well as acyclic system. The cyclic and acyclic molecules undergoes various types of reactions that can be studied for dynamic stereochemistry. One of those important reactions is the substitution reactions. Substitution reactions, you know, are those reactions in which one atom or a group of atoms in a chemical compound is replaced by another atom or a functional group. It can be mainly of three types, that is electrophilic substitution reactions, nucleophilic substitution reaction, or free radical substitution reactions. Let us see now first nucleophilic substitution reactions. In nucleophilic substitution reactions, the strong nucleophile displaces a weak nucleophile in a chemical reaction, and the reactivities between any two reactants will depend on the mechanism they follow to give the product. Do you understand? Now we are actually relating the stereochemistry with the rate of the reaction. So here the rate will depend on the reactivities of the two reactant, and that reactivity will depend on the stereochemistry of the reactant. Now this is also applicable to stereoisomers here, which reacts to give a stereospecific or stereoselective product. For example, in the following reaction where RL, L actually represents here the leaving group, the nucleophile is attacking this RL molecule, whereby the nucleophile gets attached to R and L leaves as L negative. Now L being the leaving group, it can be any leaving group, like it can be bromide or iodide or sulfide or any other, and the nucleophile is one which can be either negatively charged as shown here, or it can be a neutral species which is electron rich. Now the stereochemistry of formation of this RNU, that is nucleophile attached to this R group from RL, depends on the mechanism they took during its formation. The reaction may proceed either by SN1 mechanism or SN2 mechanism based on the type of the reactions involved. Let us see how SN1 will proceed. SN1 actually stands for substitution, nucleophilic, unimolecular. So one stand here for unimolecular. So SN1 proceeds via a carbocation formation. The nucleophile attacks this carbocation. Because carbocation is a planar species and it is a sp through hybridized species, so it can be attacked from each face, either from the top or from the bottom, ultimately leading to complete loss of stereochemistry at the reactive center. This is shown in the following scheme. You can see the nucleophile can either attack from the top face or from the bottom face. Ultimately, both the possibilities are equally probable, so we are ultimately having complete loss of stereochemistry. There is no specificity in this scheme. So the products obtained are with complete 50% retention and 50% inversion. The products are completely non-stereospecific. But in a cyclic system, the mechanism is affected by the axial equatorial positions of hydrogen. For example, in the acetylysis of cis and trans tertiary-butyl cyclohexyl tosylates, as shown in this scheme represented as A and B, you can see the 1,3 diaxial interactions leads to a faster SN1 reaction. Can you see there is 1,3 diaxial interaction in case of cis tosylate, and this is absent in trans tosylate. So in cis tosylate, when the nucleophile is attacking from the back side, this is completely unhindered. So the nucleophile can easily react, and therefore the SN mechanism is faster in case of cis. Whereas in case of trans, there is no 1,3 diaxial interaction, but the incoming nucleophile will be facing that hindrance due to 1,3 diaxial interaction, and hence the rate becomes slower. So in this case, cis isomer, the tosyl group are at the axial position, which has 1,3 non-bonded interaction with axial hydrogens, leading to a faster SN1 than the trans isomer. Let us now study the nucleophilic substitution bimolecular, which means SN2 mechanism. In SN2, it is a substitution reaction which proceeds in a single step, or we can say it is a concerted mechanism. and this proceeds via a formation of penta-coordinated transition state of the carbon atom involved on the attack. So the carbon atom which is attacked will have a pentavalent transition state. Now this sp3 hybridized carbon atom in the react where the bond breaking has to occur, the bond formation takes place simultaneously, giving you a 5 or penta-coordinated transition state. And this, both the bond breaking as well as bond forming is happening simultaneously. In this reaction, the rate of reaction depends on both the concentrations, that is the concentration of the reactant as well as the concentration of the nucleophile. Therefore, the reactivity of all those compounds which proceeds through nucleophilic substitution by molecular process depends on the stability of the transition state. The more stable is the transition state, the faster would be the reaction rate. You can see this in the following scheme, and in these cases the nucleophile attacks the substrate from the opposite side to the position of the leaving group, resulting in the inversion of configuration. So you can see in SN1, because the nucleophile could have attacked from both the top as well as the bottom face, there was no stereochemistry, there was no stereospecificity. But in case of SN2, because the leaving group has not yet departed, but the attacking group has already started to form the bond with the carbon center, so here we will only have the backside attack leading to complete inversion of configuration as shown in the figure. Now in case of cyclohexane derivatives, the SN2 reaction involves a transition state in which the penta-coordinated carbon atom to which the leaving group is attached and the incoming nucleophile are partially bonded as shown in the figures here. The main interaction is between the nucleophile and the two axial hydrogens and between X and the two axial hydrogens in figure 2. So for the trans and cis isomers respectively. Now if the nucleophile is bulkier than X, the transition state in figure 1 will be of higher energy, because the nucleophile has to come always from the back side of the X. So if it is bulky, this is going to face the 1,3 diaxial interactions. So it is of higher energy than the transition state in figure 2, and the equatorial isomer react at a slower rate. Thus, for 4-tertiary butyl cyclohexyl bromide, the cis isomer will react approximately 60 times faster than the trans isomer, because in cis isomer the nucleophile, which is bulky, is coming from an unhindered side, so it will go faster. Whereas in case of trans isomer, the nucleophile is coming from the hindered side and it is going to slow down the rate. So the scheme has been shown with the nucleophile as the sulfide ion, phenyl sulfide ion, and the reaction is carried out in aqueous ethanol. So phenyl sulfide ion, being a bulky nucleophile, will definitely have a slower rate in the trans isomer as compared to cis isomer. Most of the substitution reactions proceed either via racemization or by inversion of configuration. But there are nucleophilic substitution reactions which proceed via 100% retention of configuration. So can you imagine how 100% retention of configuration could be achieved? Actually, this type of reaction involves 2 SN2 processes. So one SN2 process will give you inversion of configuration. The second SN2 process will give another inversion of configuration. So in all, there will be net retention of configuration. And this happens in the process known as neighboring group participation, or in short, simply the NGP. The reaction which proceeds via such type of participants has shown to have enhanced rate of reactions. For example, look at the following scheme. Here, the 5-methoxytosylates undergo acetylosis faster than N-hexyl tosylates. and this is because of the neighboring group participation of the oxygen atom of the methoxy group. So can you see, because the oxygen is first of all attacking on the carbon atom where the tosylate was present, so tosylate leaves, and when the nucleophile again come to that carbon atom, the methoxy oxygen goes back. So it is a two-step SN2 processes. Inversion and inversion ultimately lead to retention of configuration. In another example, sulfur mustard, there is a compound as shown in this scheme. The sulfur mustard reacts with NaOH faster than 1,5-dichloropentane, and this also is because of the neighboring group participation from sulfur atom. As it is seen, the sulfur atom first attacks the carbon atom whereby chlorine is leaving, and then when the nucleophile attacks, the sulfur bond is again broken, ultimately leading to complete retention of configuration, and the reaction rate goes much faster. This neighboring group participation is increasing the rates of the reactions. Also, the participation of the double bond can also help in removing a leaving group. It's not only oxygen or sulfur or any other heteroatom with the lone pair, but the double bond can also help as neighboring group participation, and it aids in departing of the leaving group, but only if it is suitably oriented in favor of neighboring group participation. Let us see, for example, the relative rates of acetylysis of the three norborane derivatives as shown in this figure in A, B and C. These are different tosylate or norborane derivatives. The N-tosylate, which is represented by B, reacts 10 raised to the power 11 times faster than the norboronyl tosylate A, which provides the double bond participation in the form of neighboring group participation to form the non-classical carbocation, which only react to form the right hand side, giving an acetate having the complete retention of configuration. So you can see, because of the double bond, the carbocation gets stabilized, the tosylate can leave faster, as fast as 10 raised to the power 11. When there was no double bond, the reaction was much slower, and now because of the presence of double bond, this double bond is assisting the reaction by the way of neighboring group participation, and this has enhanced the rate of the reaction. Now the C part, look at the C tosylate here, there is no neighboring group participation. Why? Because the tosylate and the double bond are present in the same direction, so it cannot have enchimeric assistance. But this C, the syn isomer, it dissociates without enchimeric assistance into homoallylic carbocation as shown in the following scheme. And this homoallylic carbocation rearranges to give you an allylic carbocation and ultimately leads to the formation of the bicyclic product D. This reaction is also 10 raised to the power 4 times faster as compared to the reaction of tosylate A. And this faster reaction can be attributed due to the sigma bond electron participation. It is not the double bond, but the sigma bond electron participation. Now, this kind of double bond participation or neighboring group participation is also seen or observed in phenyl rings. The pi bond of the phenyl ring also participate in neighboring group participation to form an intermediate phenonium ion, that is phenyl carbocation. The 2s, 3s, 3o, 3-phenyl 2-butyl tosylate as shown in this scheme on solvolysis in acetic acid gives 96% of the racemic mixture of the 3o acetate. Now the remaining 4% is erythroacetate, and this was formed by direct SN2 reaction. So the 96% product is obtained by the neighboring group participation of the phenyl ion, and the 4% is obtained by the direct SN2 reaction. Whereas the erythroisomer, that is 2R3S, on similar treatment gives only the erythroacetate as shown in this figure. So you can see the phenyl ion is also participating in the neighboring group participation and enhancing the depart of tosylate ion, and thereby increasing the rate of the reaction and also affecting the final outcome of the reaction. So now you have understood the stereochemical aspects or the effect of stereochemistry or dynamic stereochemistry on the substitution reactions. Now let us move on to elimination reactions and see how this dynamic stereochemistry also affects the elimination reactions. You know that the stereochemistry of three types of elimination reactions, which you have already studied, I think. These reactions are E2 elimination, cis-elimination, and the third one is 1,4 elimination. Let us study these one by one. In E2 elimination, the E2 elimination reaction is also known as the bimolecular elimination reaction. So in this case, the rate determining step will involve an interaction between the two species, a reactant and a reagent, or maybe both the reactants. For a reaction between an alkyl halide and a base, as shown here, the rate determining steps involves an interaction between the base as well as on the alkyl halide, and the reaction takes place in a concerted way. That means the abstraction of the proton by the base and the departure, or we can say the X being departing at the same time when the base is abstracting the proton from the carbon, ultimately leading to the formation of C double bond C, that is alkene. Now this simultaneous removal of the proton by the base and the loss of leaving group X for the formation of the pi bond takes place in E2 mechanism. This E2 mechanism is somewhat you can say very similar to the SN2 mechanism, where the two things were happening at the same time in a concerted way. So in this case, the base is abstracting a proton in the same time or at the same time when X is leaving the carbon. So this mechanism of the reaction can be represented in this way as shown in the following scheme, wherein an alkyl halide is attacked by a base. The base is abstracting a proton from completely an opposite, diagonally opposite side from which the leaving group is departing. The rate of elimination here depends on the concentration of both the base, which is the substrate, and the reactant, which is your alkyl halide. And this is kinetically a second order reaction, first order with respect to substrate and first order with respect to the base. Thus, in the rate expression, both the substrate, which is an alkyl halide, and the base are involved, and it can be written as rate is equal to some constant K into the concentration of alkyl halide into the concentration of the base. In this E2 elimination reaction, it was observed that the dehydrohalogenation is an anti-elimination. Okay, so the base is abstracting the proton from one side and X is leaving from the diagonally opposite side. In this case, if we start from erythrohalide, it was observed that this erythrohalide only gave the Z alkene, whereas the triohalide gave only the E alkene. So you can determine the stereochemistry by understanding the mechanism of this elimination reaction. Now let us understand cis-elimination. The cis-elimination usually takes place by pyrolysis. Pyrolysis means the breaking of bond by application of heat. The pyro means heat. So the pyrolysis of esters, let us say for example acetate ester, or let us say methyl xanthate ester, that takes place via cis-elimination as shown here in this figure, ultimately leads to the formation of alkenes. And this happens via a cyclic transition state, whereby the oxygen atom of or the carbonyl group of the ester attacks the hydrogen in a cyclic form, ultimately forming a 6-membered ring. As you can see in this figure, there is a 6-membered ring transition state that is happening due to the abstraction of proton by the carbonyl oxygen atom from the carbon atom which is leaving its electron pair to form a carbon double bond carbon, ultimately giving you an alkene. So, in this cyclic system, like let us say cyclohexane system, the axial equatorial alignment also plays an important role. Let us see in cyclohexane, for example, pyrolysis of both the cis and trans isomer of cyclohexane derivative, they gave the same product. As you can see in this reaction, the 1-para-alkyl sulfonyl 1-cyclohexane is the final product. Either we start from trans compound or we start from the cis compound, the product in both the cases are same. The trans compound undergoes cis-elimination, whereas the cis compound undergoes trans-elimination, and that is why the product is same. So, this is what is happening when you are having different reactions or different reactants with different stereochemistry. They ultimately give you a different mechanism, and that will determine what will be the stereochemistry of the product. Now let us see 1,4 elimination reaction. This is also known as fragmentation, whereby we are eliminating the small group and leading to the formation of an alkene or a double bond in the final product. This is also an example of Grob fragmentation. The Grob fragmentation has strict bond geometry requirements. That means there has to be proper orientation for this elimination to occur. This is stereospecific towards the double bond formation, and it happens most easily when the reactant is conformationally locked in 1,3 difunctionalized compounds. As you can see in the following scheme, the breaking of CX bond and the CC bond are aligned in an anti-periplanar stereochemistry. When the CX bond is breaking and the bond between OH is also breaking because the base is abstracting the proton, and the C double bond C bond, as you can see it is a highlighted bond, this has to be anti-periplanar, and this reaction ultimately leads to the ring opening only if this kind of stereochemistry or the proper reactant orientation is present. So, let us summarize what we have learned in this module. First of all, the dynamic stereochemistry, we have understood what this term actually means. This dynamic stereochemistry deals with the studies of effect of stereochemistry on the rate of chemical reactions. The dynamic stereochemistry is based on stereoselective reactions and stereospecific reactions. The reactions are explained by taking the examples of substitution as well as elimination reactions. In the nucleophilic substitution reaction, the reactivities between any two reactants depend upon the mechanism they follow to give the product. And this is also applicable to the stereoisomers, which reacts to give a stereospecific or stereoselective products. Similarly, in E2 elimination reactions, it was observed that the dehydrohalogenation of the erythrohalide gave only Z-alkene, whereas the stereoisomer gave only the E-alkene. The cis-elimination usually takes place by pyrolysis, and the pyrolysis of esters like acetate ester or any other ester takes place by cis-elimination, leading to the formation of olefins, and this go via a cyclic transition state formation. And lastly, the 1,4 elimination, also known as Grob fragmentation, has strict bond geometry requirements. Only then this elimination will take place.